Below in this lecture, we'll answer two questions. In the first question, we find out the area of this green shape using two different methods. And in the second question, we find out the area of this circle that intersects with this right triangle ACP. So, let's start with the first question. In the drawing, we have quarter circle AOB. Side OB equals to 2 units in its length. This is line segment AD. That equals to this line segment DO. And this is angle DCB, that is the right angle, and therefore the green triangle DCB is the right angle. So we have to find out the area of this green shape, that is actually the area of the right green triangle DCB. So first of all, AOB is a quarter circle, and therefore this is the right angle. Angle AOB is the right angle. In addition, in quarter circle AOB, OB and OA, they're both the area of the quarter circle. And the radius OB equals to 2, and therefore the radius OA must be also equal to 2 units in its length. The radius AO is equals to 2. The radius AO has been bisected at point D into two halves. The first half AD equals to the second half DO. And each half must be equal to 2 over 2. So the first half AD equals to 2 over 2, that is 1. And the second half of the radius AD must be also equal to 1 unit in its length. In the next step, we will implement the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So according to the Pythagoras theorem, this right triangle DOB DB square, that is the square of the hypotenuse, equals to DO square plus OB square. Repeat again, according to the Pythagoras theorem, in this right triangle DOB, DB square, that is the square of the hypotenuse, equals to DO square plus OB square. DB is the missing side, so we leave it as it is. So it is DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1. Plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So total actually found out that OB square equals to 1 plus 4, that is 5. OB square equals to 5. Here we take a root out of this equation and find again that the length of the hypotenuse OB is equal to the square root of 5 units. This is the hypotenuse. Actually, it is dB square equals to 5. This dB square equals to 5, hypotenuse dB, and therefore dB equals to the square root of 5 units in its length. This is the hypotenuse dB, this equals to the square root of 5 units in its length. In the next step, we will do a construction. That is to say, we will complete this quarter circle to a circle. So completed the quarter circle to a circle, and we'll extend the radius BO by sideline until it touches the circle. We will define the touching point of the extended radius BO with this circle. This point is point P. The radius BO is a radius, it is absolutely a straight line. When you extend a straight line by straight line, the result BP must be also a straight line. So BP is a straight line that touches the circle at those 2 points, P and B, and therefore BP is a chord. But BP is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore PB is the diameter of this circle. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle, that is equals to 2 units in its length. The next step, we will extend the radius OEO, we will extend the radius AO of this circle by sideline until it touches the circle. And when you find the touching point of the extended radius AO with this circle, this point is point Q. The radius AO is the straight line. When you extend the straight line by straight line, the result AQ must be also a straight line. AQ is a straight line that touches the circle at those 2 points A and Q, therefore AQ is also the diameter of this circle. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle that equals to 2 units in its length. So, as you know, if you found out that AQ is also the diameter of the circle, in the next step, we will extend side CD of this rectangle DCB by sideline until it touches the circle. But the question is here where the extended side CD will touch the circle. We will assume that the extended side CD will touch the circle, not touch the circle at point P, but at this point, point N. So according to our assumption, we have here Triangle DCN. It is triangle BCN. This is triangle BCN. Triangle BCN is equal to 90 degrees in size, and triangle BCN subtend on this chord called BN. This is chord BN. Chord BN is definitely not the diameter of the circle because of the fact that chord BN doesn't pass through point O, that is the center of the circle. And we know that any chord that doesn't pass through the center of the circle cannot be the diameter of the circle. So therefore, BN is not the diameter of the circle. So according to our assumption that the extended side CD will touch the circle at point N, we have here triangle BCN. This is equal to 90 degrees inside according to what is given us in the question. And triangle BCN subtend on chord BN, that is definitely not the diameter of the circle. So it is a contradiction to rule 5. Why? Because according to rule 5, any triangle that is equal to 90 degrees in size, like this triangle, must subtend on the diameter of the circle. But triangle BCN subtend on chord BN, that is not the diameter of the circle. So, a bit quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So in the problem we have a circle. This is peripheral angle MAN. That is equal to 90 degrees in size, and indeed peripheral angle MAN subtend on chord MN, that is the diameter of the circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. Repeat again that this is triangle BCN that is equal to 90 degrees in size, and it doesn't subtend on the diameter of the circle. So it is a contradiction to rule 5. Due to the contradiction to rule 5, we must conclude that the extended side CD will not touch the circle at this point, point N. In the next step, we will assume that the extended side CD will touch the circle at this point, point M. So according to our assumption, we have here triangle BCM. This is triangle BCM. This is equal to 90 degrees in size, and it subtends on chord BM. Chord BM is definitely not the diameter of the circle because of the fact that chord BM doesn't pass through point O, that is the center of the circle, as we know that any chord that doesn't pass through the center of the circle cannot be the diameter of the circle. So again, we have a contradiction to rule 5. Well, because we have here triangle BCM that is equal to 90 degrees in size, it doesn't subtend the diameter of the circle, because chord PM is not the diameter of the circle. So due to the contradiction to rule 5, we will conclude that the extended side CD will not touch the circle at this point, point M. And therefore, we will conclude that the extended side CD will touch the circle at this point, point P, and not in any other point. Otherwise, we have contradiction to rule 5. So now we don't have contradiction to all 5 anymore. Why? Because we have here peripheral angle BCP that is equal to 90 degrees inside, and indeed it's subtend on on chord PB, that is the diameter of the circle. We already found out that chord PB is the diameter of the circle. Then again, we have here peripheral angle BCP that is equal to 90 degrees in size, according to what is given in the question, and indeed peripheral angle BCP subset on chord PB, that is the diameter of the circle, exactly according to all 5. PB is the diameter of the circle, and therefore it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to all 3. All 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is the right angle, plus this missing angle. In total the sum of those 2 angles must be equal to 180 degrees. 180 degrees according to all 3. Therefore this missing angle must be equal to 90 degrees in its size. So this is the right angle PDO. This right angle PDO, DO equals to 1, OP equals to 2, and therefore the hypotenuse must be equal to 5, exactly like this right triangle, with the same sides 1, 2, and then when you have 2 perpendiculars that equals to 1 and 2, then the hypotenuse must be equal to the square root of 5. So the hypotenuse PD of this right triangle PDO is equal to the square root of 5 units in its length. So here we will implement all 24 in our drawing. So I put quickly on all 24. All 24 is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So in the drawing, we have a circle. This is chord AB that intersects with chord CD at point O. So in this drawing, the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement all 24 in our drawing. Why? Because in our drawing, chord AQ, AQ is a chord because it is the diameter of the circle. It is actually the biggest chord in the circle. So chord AQ intersects with this chord CP at point D. Why CP is a chord? Because of the fact that we extended the straight line CD by straight line, and therefore the result CP must be also a straight line. But CP is a straight line that touches the circle, those 2 points, C and P. Therefore CP is a chord. Again, chord AQ intersects with chord CP at point D. So all the requirements of all 24 are satisfied, and therefore we can implement here all 24. So now if you found out that chord AQ intersects with called CP at point D. The intersection point occurs at point D. And again, now original drawing called AQ intersection called CP at point D. So all the requirements of Rule 24 are satisfied, and therefore we can implement here Rule 24. According to Rule 24, the following equation is true. AD times DQ equals to CD times DP. And again, the following, according to Rule 24, the following equation is true. AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times dp. dp equals to the square root of 5 units in its length. So in total, we found out that according to Rule 24, 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to CD times square root of 5. Here we divide this equation by square root of 5 and find that the missing side CD is equal to 3 over square root of 5 units in its length. And again, we should find out that this is the missing side CD, that is equals to 3 over square root of 5 units in its length. In the next step, we will implement the Pythagoras theorem. This right green triangle DCB. That is the area that we are looking for in this question. In this right triangle DCB, here by PT is abbreviation for Pythagoras theorem. In this green right triangle DCB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to dc squared plus cb squared. And again, in this right triangle DCB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to dc squared plus cb squared. dc equals to 3 over square root of 5, therefore dc squared equals to 3 over square root of 5 squared, that is actually 9/5. So dc squared equals to 9/5. dB is, equals to 5, and therefore dB squared equals to the square root of 5, therefore dB squared equals to the square root of 5 squared, that is 5. So dB squared equals to 5. So 5 equals to dc squared equals to 9/5 plus cb squared. cb is the missing side, so we leave it as it is. So in total, if you found out that 5 equals to 9/5 plus CB squared. Here we multiply 5 by 5 and then we divide it by 5 in order to come in front of with this number. 5 times 5 is 25 over 5. We multiply it by 5 and then we divide it by 5, so we change nothing. So 25 over 5 equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation and you get that 25/5 minus 9/5 is 16/5 equals to CB squared. Here we take a root out of this equation and finally get that the missing sign CB is equal to the square root of 16, that is 4, over square root of 5 units in its length. So this is the missing side CB. This equals to 4 over square root of 5 units in its length. Now it is very easy to find out the area of the green shape. The area of the green shape, it is actually the area of this green rectangle DCB. And again, the area of the green shape, this is the area that we are looking for this question. It is the area of the green rectangle, triangle DCB. And the area of the green rectangle DCB is equal to the base DC times the height CB over 2. And again, the area of this green rectangle DCB, it is equal to the base DC times the height CB over 2. The base DC equals to 3 over square root of 5 units times the height CB equals to 4 over square root of 5 units divided by 2. So in total, if you found out that the area that we are working for in this question, that is the area of the green shape, equals to 3 over square root of 5 times 4 over square root of 5 divided by 2. 3 times 4 is 12. Here we have square root of 5 times square root of 5 is 5 divided by 2. We have 12 over 5 over 2. We will move 2 to the denominator. This expression in total equals to 12 over 5 times 2. This is to say it is 12, 5 times 2 is 10. So it is 12 over 10 or 12 tenths. 12 tenths is 1.2 square units in size. So in total, we found out that the area that we are looking for in this question, that is the area of the green shape, the area of this green shape equals to 1.2 square units in its size. So we finish with the first method. In the next step, I present to you how to find out the area of this green shape according to the second method. We only found out in the first method that OB and OA, they are both the radii of the quarter circle. Each of them is equal to 2. Because the radius of this quarter circle equals to 2. The radius OA equals to 2 units in its length. At point D, the radius AO is being bisected into two halves. The first half AD equals to 1, and the second half D also equals to 1 unit in its length. AOB is a quarter circle, and therefore this angle is a right angle. In the next step, we will complete this quarter circle to a semicircle. We'll extend the other BO by sideline until it touches the semicircle. We define the touching point of the extended radius BO with this semicircle. This point is point P. The radius BO, it is absolutely a straight line. When you extend the straight line by straight line, the result BP must be also a straight line. BP is a straight line that touches the semicircle, those 2 points, B and P. Therefore, BP is a chord. BP is a chord that passes through point O, that is the center of this semicircle. And we know that any chord that passes through the center of the circle or semicircle must be the diameter of the semicircle or circle. So BP is the diameter of this semicircle. In the next step, we will extend side CD by sideline until it touches the semicircle. I've already proved to you that the extended side CD must touch the semicircle at point P and not in any other point due to the contradiction to Rule 5. And again, the extended side CD must touch the semicircle at point P and not in any other point. Now we don't have any contradiction to Rule 5 anymore because we have peripheral angle BCP, that is the right angle according to what is given as the question. Peripheral angle BCP subtend on chord PB, that is the diameter of the semicircle, exactly according to Rule 5. This is the right triangle PDO. We already proved that in method 1 that this angle equals to 90 degrees in its size according to Rule 3. So in the right triangle POD, point O is the center of the semicircle, point P is the point of the semicircle itself, therefore OP is the radius of the semicircle, that is equals to 2. According to the Pythagoras theorem, the opponent's PD must be equal to the square root of 5 units in its length. Because we have 2 perpendiculars with 2 and 1, and therefore the opponent, according to the Pythagoras theorem, must be equal to the square root of 5 units in its length. This is the right triangle PDO. We define this angle DPO as alpha. So in this right small triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this part, this angle must equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. According to the symbol that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that this is the right triangle PDO. It is similar to this big right triangle PCB. Again, we prove that this small right triangle PDO is similar to the big right triangle PCB. So why those two right triangles are similar to each other? First of all, this is the angle alpha. This is the common angle that belongs to both triangles. So we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees once alpha and therefore they are equal to each other. So we should prove that all the figures of this small right triangle PDO are corresponding equal to all the figures of this big right triangle PCB, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. We should prove that this is the right small triangle PDO. And is similar to this big right triangle PCB. According to angle similarity rule. But again, the right small triangle PDO is similar, this is the sign of similar, to the right big triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we know that the following relationship exists between their sides. We derive that side PD of the small right triangle PDO over side PB of this big right triangle PCB is equal to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle PDO over side PC of this big right triangle PCB. So, continue on. Okay, again, from the fact that this small right triangle PDO is similar to this big right triangle PCB, we derive that the following relationship exists between their sides. We derive that side PD of the small right triangle PDO or side PB of the big right triangle PCB is equal to side DO of the small right triangle PDO or side CB of the big right triangle PCB. It is also equal to side PO of the small right triangle PDO or side PC of the big right triangle PCB. PD equals to the square root of 5 units over PB. PB in total equals to 2 plus 2, that is 4. And it is equals to DO. DO is 1 over CB. CB is the missing side, so we leave it as it is. And it is also equals to PO. PO is 2 over PC. PC in total equals to the square root of 5 plus DC. So in total, if you found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other. Therefore, we get the first equation from those two sides. According to the first equation, we get that square root of 5 over 4 equals to 1 over CB. So, as you know, according to the first equation, square root of 5 over 4 equals to 1 over CB. Here we will cross multiply this equation, equation 1, and get that according to this equation, equation 1 times 4 is 4, equals to the square root of 5 times CB. Here we will divide this equation, equation 1 by square root of 5, and find here that according to this equation, equation 1, the missing side CB equals to 4 over square root of 5 units in its length. This is the missing side CB. This is equals to 4 over square root of 5 units in its length. Those two sides of the equation are also equal to each other. So we get the second equation from those two sides that are equal to each other. So according to equation 2, we get that square root of 5 over 4 equals to 2 over square root of 5 plus DC. So I write it down. According to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. This is equation 2. So here we will cross multiply this equation, equation 2. And get that according to equation 2, 2 times 4 is 8. So 8 equals to square root of 5 times square root of 5 plus DC. So according to equation 2, 8 equals to the square root of 5 times the square root of 5 is 5, and we have square root of 5 times DC plus square root of 5 times DC. So total we found out that according to equation 2, 8 equals to 5 plus square root of 5 times DC. Here we subtract 5 from this equation, equation 2. We get that according to equation 2, 8 minus 5 is 3, equals to the square root of 5 times DC. Here we will divide this equation, equation 2 by square root of 5, and find that according to this equation, equation 2, the missing side DC is equal to 3 over square root of 5 units in its length. This is the missing side DC is equals to 3 over square root of 5 units in its length. Now it is very easy to find out the area of this green shape. This is actually the area of this right triangle DCB. The area of the given right angle DCB is equals to the base DC times the height CB over 2. So I write it down. The area of the green shape is actually equals to the area of the green right angle DCB. And the area of the green right angle DCB, the area of this green triangle DCB, it is equals to the base DC times the height CB over 2. And again, the area of the green right triangle DCB equals to the base DC times the height CB over 2. DC equals to 3 over square root of 5 units times CB equals to 4 over square root of 5 units divided by 2. So in total, if you found out that the area of the green shape equals to the area of the green right triangle DCB, and the area of the green right triangle DCB equals to the base DC times the height CB over 2. DC is 3 over square root of 5 times CB, that is 4 over square root of 5 divided by 2. Here we have in the numerator 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. So here we move 2 to the denominator. So this expression in total will be equal to 12 over 5 times 2. So it is 12 over 5 times 2, that is 10. So the total, the area of the green shape equals to 12 tenths. In terms of numbers, it equals to 1.2 square units in size. So in both methods, we found out that the area that we are looking for in this question, that is the area of this green shape, in total it is equals to 1.2 square units in size. So finish with the second method. And the first question. The next step, I present you the second question and we solve the second question of this lecture. Our task in the second question is to find out the area of this circle. So in the drawing we have a circle that intersects with this right triangle ACP at those 2 points. This is line 7 BC. This is equals to 1 unit in its length. This is line 7 CP. This is equal to 4 units in its length. This is angle ACP. That is a right angle. And in addition, we have from the common point, point 3, we have two tangents to this circle, tangent PB and tangent PA. So therefore, we can implement here rule 2. So on page 15 on rule 2, according to rule 2, the lengths of two tangents from a common point to a circle are equal. So in the drawing, we have a circle. This is the common point, point P. From this common point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, the length of tangent PA is equal to the length of this tangent PB. So PA equals to PB. So you can actually implement rule 2 in our drawing. Because in our drawing, this is the common point, point P. From this common point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So I write it down. From the common point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. According to rule 2, of course. But it is given us the question that the length of tangent PB in total equals to 1 plus 4, that is 5. So we can write here that PB equals to 5 units in its length. And from this equation, PA equals to PB equals to 5, we will derive that PA also must be also equal to 5 units in its length. This is tangent PA, this is equals to 5 units in its length according to rule 2. In the next step, we will implement the Pythagoras theorem on this right triangle ACP. Here by PT is the abbreviation for Pythagoras theorem. In this right triangle ACP, according to the Pythagoras theorem, 8p squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. And again, this right triangle ACP, according to the Pythagoras theorem, the following equation is true. That 8p squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP equals to 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So total we found out that 25 equals to AC squared plus 16. Here we will subtract 16 from this equation and get that 25 AC squared equals to 25 from 16 is 9. So AC squared equals to 9. Here we take out of this equation and find out that the missing side AC is equal to the square root of 9, that is 3. This is the missing side AC. This is equals to 3 units in its length. In the next step, we will define the center of this circle. This point is point O. We will define the radius of this circle as x. Point B is the point of tendency of tangent PB with this circle. We will join points O and B together by a straight line. Point O is the center of this circle. Point B is the point of the circle itself. Therefore, OB is the radius of this circle. This is equals to x according to our definition. The radius OB is equals to x. The radius OB is going to point B. That is the point of tendency of tangent PB with this circle. And whenever you have a radius that is on to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. BP is a tangent, so BP is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line BP at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angle we have at the upper side of BP at point C? We have this angle that is the right angle, plus this missing angle, and total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say, from point O, we will draw perpendicular on AC. Again, from point O, we will draw perpendicular on AC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. By doing this construction, we get the quadrilateral OMCB. Inside quadrilateral OMCB, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral OMCB we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM, but BC is 1, therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle OMCB, side OB must be equal to the opposite side MC, but OB is x, therefore the opposite side MC must be also equal to x units in its length. What is the length of this missing line segment? Line segment AM. From the drawing, it is very easy to see that AM total must be equal to AC minus MC. So I'll write it down. AM equals to AC minus MC. So AM in total equals to AC, that is 3, minus MC, that is x. So total AC equals to 3 minus x units in its length. AM equals to 3 minus x units in its length. In the next step, we join points O and A together by a straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of this circle. This is equals to x according to our definition. In the next step, we will implement the Pythagoras theorem on this right grand triangle, triangle AMO. Here by PT is the progression for Pythagoras theorem. This given outline AMO according to the Pythagoras theorem. AO squared, this is the square of the hypotenuse, equals to AM squared plus OM squared. And again, this again outline AMO according to the Pythagoras theorem. AO squared, this is the square of the hypotenuse, equals to AM squared plus OM squared. AO equals to x, therefore AO squared is x squared. And it is equals to AM squared. AM equals to 3 minus x, and therefore AM squared equals to 3 minus x squared. Plus OM squared. OM equals to 1, therefore OM squared equals to 1 squared, this is 1. So in total, if you found out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x plus 1. Here we have x. We have x squared on both sides of this equation, so x squared will get cancelled, after cancel x squared, on this side of the equation is left in nothing, that is to say 0. While on the other side of the equation, we have 9 plus 1, that is 10, on 6x. So in total, if you found out that 0 equals to 10 on 6x. Here we add 6x to this equation, and find that 6x equals to 10. Here we divide this equation by 2, and find that 6x over 2 is 3x, and it is equals to 10 over 2 is 5. So in total, if you found out that 3x equals to 5, here we divide this equation by 3, and we get that x equals to 5 thirds. That is to say, if you found out that the radius of this circle, x equals to 5 thirds units in its length. Here our test is to find out the area of this circle. The radius of this circle is x. The area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius is x, therefore the radius squared is x squared. So in total, if you found out that the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 5 thirds, and therefore x squared is 5 thirds squared. So in total, if you found out that the area of our circle equals to pi times 5 thirds squared. So it is pi times 5 thirds squared. 5 thirds squared equals to 5 squared is 25, over 3 squared is 9. So to that, we found out that the area that we are looking for in this question, that is the area of this circle, is equal to either 25 pi over 9 square units in size, or in terms of numbers, is equal to 8.73 units in its size. 8.73 square units in size. And then again, we should find out that the area of this circle, that is the area that we're looking for in this question, it is equal to area of 25 pi over 9 square units in size. In terms of numbers, it is equal to 8.73 square units in size. So we finish with the second method and the first question. And then finish with the second question. So, in the next step, I'll summarize the lecture. That is to say, I'll repeat on the solution of the first question with the two methods, and then repeat on the solution of this second question. In the first question, our task was to find out the area of this ring shape. So in the drawing, we have a quarter circle AOB. This is side OB, this is equals to 2 units in its length. In addition, we know that 97 AD equals to 97 DO. This is angle BCD, this is the right angle, and therefore sine BCD is the right angle. So our task was to find out the area of this ring right triangle BCD, because the ring shape is there, this right triangle BCD. So we have to find out the area of this ring right triangle BCD. This is the area of the ring shape. First of all, it is given as the question that AOB is a quarter circle, and therefore this is a right angle. In addition, we know that OB equals to OA. They are both the area of the circle, of the quarter circle. This equals to 2. Therefore, the radius OA must also equal to 2 units in its length. This is point D. That is the midpoint of this radius AO. That is to say, it's point D. The radius AO has been bisected into two halves. The first half is AD, and it is of course equal to the second half, that is DO. Each half must be equal to 2 over 2, that is 1. So AD equals to 1, and DO also equals to 1. The next step, we implement the Pythagoras theorem on this right triangle DOC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the quadratic rows. So in this right triangle DOB, it means that DB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. And again, the right triangle DOB, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to DO squared plus BO squared. DB is the missing side, so we leave it as it is. So it is DB squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 2. So we found out that DB squared equals to 1 plus 4, that is 5. So DB squared equals to 5. Here we have to go down to this equation. Finally found out that the length of the hypotenuse DB is equal to square root of 5 units in its length. This is the hypotenuse DB on the right triangle DOB, and it is equal to the square root of 5 units in its length. In the next step, we did the construction, that is to say, we completed this quarter circle to a circle, and then we extended the radius BO by a straight line until it touches the circle. At this point, we find the touching point of the extended radius BO with this circle, this point is point P. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle, and this goes to 2. BO is a radius of this circle, so BO is a radius, it is absolutely straight line. Then we extended the straight line BO by straight line. The result BP must be also a straight line, because when you extend the straight line by straight line, the result must be also a straight line. So BP is also a straight line, but BP is a straight line that touches the circle at those 2 points, and therefore BP is a chord. BP is a chord that passes from point O to the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle, and therefore chord BP is the diameter of the circle. Likewise, we extended radius AO by straight line until it touches the circle, and we find the touching point of the extended radius AO in this circle. This point is point Q. So, for the same reason that PB is the diameter of this circle, AQ must be also the diameter of the circle. I'll not repeat on the same explanation. Again, point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle, that equals to 2. Okay. So here we implemented all 24 in our drawing. Repeat all 24. Running to all 24. All 24 is drawn in any circle, so in any circle, of course, the AB intersects with chord CD at point O. Then the following equation is drawn that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So in the drawing, we have a circle. This is chord AB that intersects with chord CD at point O. So in this drawing, the following equation is drawn that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement all 24 in our drawing. Why? Because in our drawing, AQ is the diameter of the circle, and therefore it is a chord, it is actually the biggest chord in the circle. So in the drawing we have chord AQ that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. Why CP is a chord? Because of the fact that CD is a straight line, because it is one side of the right side DCB. When we extended the straight line CD by straight line, the result CP must be also a straight line. But CP is a straight line that touches the circle at those 2 points C and P, and therefore CP is a chord. So according to rule 24, we have here chord AQ that intersects with chord CP at point D. Okay? So all the requirements of rule 24 are satisfied, and therefore can implement rule 24. So we have chord AQ that intersects with chord CP at point D. So according to rule 24, the following equation is true. AD times DQ equals to CD times DP. Again, AD times DQ equals to CP times PD. AD times DQ equals to CP times DP. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is, times DP. DP is equal to 5. So in total, if you found out that 1 times 3 equals to CD times equal to 5. 1 times 3 is 3, so 3 equals to CD times equal to 5. Here we divided this equation with equal to 5. If I found out that the missing side CD equals to 3, or equal to 5 minutes inside. This is the missing side CD. is equals to 3 over square root of 5 units in its length. In the next step, implement the quadratic theorem on this right triangle DCB. Triangle DCB. According to the quadratic theorem, in this right triangle DCB, dB squared, that is the square of the hypotenuse, equals to 3b squared plus cd squared. And again, in the right triangle DCB, dB squared, that is the square of the hypotenuse, equals to dc squared plus cb squared. dB equals to the square root of 5, and therefore dB squared equals to the square root of 5 squared, that is 5. And it is equals to dc squared. dc is 3 over square root of 5, and therefore dc squared equals to 3 over square root of 5 squared. 3 over square root of 5 squared equals to 3 squared, that is 9, over square root of 5 squared, that is 5. So in total, if you found out that 5 equals to 9/5 plus cb squared. You multiply 5 by 5 and then you divide it by 5 in order to overcome factor with this number. We multiply it by 5 and then we divide it by 5, so it changes nothing. And you actually found out that 25 over 5 equals to 9/5 plus cb squared. Here we subtract 9/5 from the equation and found out that 25/5 plus 9/5 is 16/5 equals to cb squared. Here we took out all of the equation and found out that the missing sign cb equals to 4 over square root of 5 units instead. This is the missing sign cb. This is equals to 4 over square root of 5 units instead. The area of the green shape equals to the area of this right triangle DCB. And it is equal to the base DC times the CB over 2. And again, the area of the green shape equals to the area of the green triangle DCB, and the area of this green triangle DCB is equal in total to DC times CB over 2. And it is equal to the base DC times the CB over 2. DC is 3 over square root of 5 times CB is 4 over square root of 5 divided by 2. 3 times 4 is 12, square root of 5 times square root of 5 is 5 over 2. If we move to the denominator, and if you found out that this expression equals to 12 over 5 times 2, 5 times 2 is 10, so if you found out that the area of the green shape equals to 12 tenths, that is 1.2 square units in size. And again, the area of this green shape in total it is equal to 1.2 square units in size. So we finish to repeat on the first method. The next step, repeat on the second method. Our task is to find out the area of this green shape. A or B is a quarter circle, therefore this is a right angle. O, B, and OA, they are both the area of the quarter circle, that equals to 2. At point D, the radius AO is intersected into 2 halves. The first half is 2 over 2, that is 1, so the second half must be also equal to 1. So here we completed this quarter circle to a semicircle. Then extended radius BO by third line until it touches the circle at this point, point P. When extend the third line by third line, the result BP must be also a third line. So BP is the third line that touches the circle at those 2 points P and B, therefore BP is a chord, but BP is a chord that passes from point O, that is the center of the semicircle. We know that any chord that passes through the center of the circle or semicircle must be the diameter of the semicircle or circle. So, conclusion, we should found out that PB is the diameter of this semicircle, and we extended side CD by side line until it touches the semicircle. And in the first method, we should found out that the extended side CD must touch the semicircle at point P and not in any other point due to the contradiction to Rule 5. The extended side CD must touch the semicircle at point P and not in any other point. This angle equals to 90 degrees according to Rule 3, we only found in the first method. So this right angle PDO equals to 2, because it is the radius of this semicircle. DO equals 1, and the hypotenuse DP must be equals to the square root of 5 units in its length. In the next step, we define this angle DPO, and the right angle DPO is alpha. So in the right angle DPO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles and its angles. Likewise, we focus on the big right angle PCB. This big right angle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha according to the sum rule that I have already mentioned. That states that the sum of the angles in the triangle is equal to 180 degrees. So this angle must be equal to 90 degrees minus alpha. It is very easy to see that this is the small right angle PDO that is similar to this big right angle PCB. So why those two right angles are similar to each other? First of all, this is angle alpha, that is a common angle that belongs to both triangles, so we might know that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees also, and therefore they are equal to each other. So we should find out that all the angles of this big small right angle PDO correspond equal to all the angles of this big right angle PCB. So, therefore, those two triangles are similar to each other according to angle similar to 1. Again, if you found out that the small right angle POD is equals to the big right angle PCB according to angle similar to 1. And from the fact that those two right angles are similar to each other, this is to say from the fact that the small right angle PDO is similar to the big right angle PCB, we derive that the following relationship exists between their sides. We derive that side PD of the small right angle PDO or side PB of the big right angle PBC, it is equal to side DO of the small right angle PDO or side CB of the big right angle PCB, and it is also equal to side PO of the small right angle PDO or side PC of the big right angle PCB. PD is equal to 5, PB is 4, DO is 1, CB is the missing side, so it is PO is 2, and PC in total, this is plus 7 PC, in total it is equal to the square root of 5 plus square root of 5 plus DC. Again, PC in total equals to the square root of 5 plus DC. Again, PC in total equals to the square root of 5 plus DC. So in total, we should find out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, so we get the equation 1 from those two sides. According to equation 1, we should find out that square root of 5 over 4 equals to 1 over CB. And again, according to equation 1, if we found out that square root of 5 over 4 equals to 1 over CB. Here, of course, multiply this equation. If I found out that 1 times 4 is 4 equals to the square root of 5 times CB. Here we divided the equation 1 by square root of 5 and found out that according to equation 1, CB equals to 4 over square root of 5 units in its length. Those two sides of the equation are also equal to each other, so we get the equation 2 from those two sides that are equal to each other. According to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Again, according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here, of course, multiply this equation 2, we find out according to this equation 2, 2 times 4 is 8. This equals to the square root of 5 times square root of 5 plus DC. We open the brackets here and we found out that square root of 5 times square root of 5 is 5 plus square root of 5 times DC. So in total, according to equation 2, we found out that 8 equals to 5 times 8 equals to 5 plus square root of 5 times DC. Here we subtract this 5 from this equation and we found out that 8 plus 5 is 3, so 3 equals to the square root of 5. Again, 8 times 5 is 3, so 3 equals to the square root of 5 times 0. Here we divided the equation 2 by square root of 5 times DC, of course. Here we divided the equation 2 by square root of 5 and find out that according to equation 2, DC equals to the square root of 5. This equals to 3 over square root of 5 units in its length, because we have here 5 equals to square root of 5 times DC. 8 minus 5 is 3, so here in this equation we have 5 equals to the square root of 5 times DC. Here we divided this equation 2 by square root of 5 and find out that DC equals to 3 over square root of 5 units in its length. This is side DC, is equals to 3 over square root of 5 units in its length. And we already found out that CB equals to 4 over square root of 5 units in its length. Now it is very easy to find out the area of the green shape. The area of the green shape in total equals to the area of this green rectangle DCB. Again, the area of the green shape equals to the area of the green rectangle DCB. And the area of this green rectangle DCB equals to the base DC times the height CB over 2. Again, the area of the green rectangle DCB in total equals to the base DC times the height CB over 2. DC is 3 over square root of 5 times CB is 4 over square root of 5 divided by 2. 3 times 4 is 12, square root of 5 times square root of 5 is 5 over 2. Here we move 2 to the denominator, and in total this expression equals to 12 times 5 times 12 over 5 times 2, the distance. So it is 12 tenths, so in terms of numbers it equals to 1.2 square units in size. So in both methods we have found out that the area that we are looking for in this question, that is the area of this green shape, equals to 1.2 square units in size. So we finish with the second method of the second question, and we finish with the second method of the first question. And in the next step I repeat on the solution of the second question. In the second question, our task is to find out the area of this circle. So in the drawing we have a circle that intersects with this right angle ACP at those 2 points. We know that BC equals to 1 unit in its length. This is 97 CP. This is equals to 4 units in its length. This is angle ACP. This is right angle. In addition, this is the common side point P. For this common side point P, we have 2 tangents to this circle, tangent PA and tangent PB. Again, our task is to find out the area of this circle. So first of all, we implemented rule 2 in our drawing. According to rule 2, the lengths of 2 tangents from common side point to a circle are equal. So in the drawing we have a circle, this is the common side point P. For this common side point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. This is to say PA equals to PB. So we can actually implement rule 2 in our drawing. In our drawing, this is the common side point P. For this common side point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. This is to say PA equals to PB. So again, if you focus on the common side point P, according to rule 2, tangent PA equals to tangent PB in its length. But it is given us the question that the length of this tangent PB in total it is equals to 1 plus 4, that is 5. So we can write here that tangent PB equals to 5 units in its length. And for this equation PA equals to PB equals to 5, we will have that PA must be also equal to 5 units in its length. This is tangent PA, this is equals to 5 units in its length. In the next step, we implemented the Pythagoras theorem on this right angle triangle ACP. According to the Pythagoras theorem on this right angle ACP, AP square equals to AC square plus CP square. And again, the right triangle ACP, according to the Pythagoras theorem, AP square, this is the square of the hypotenuse, equals to AC square plus CP square. AP is 5, therefore AP square is 5 squared, that is 25, and it is equals to AC square. AC is the missing side, so it is so it is AC square plus CP square. CP is 4, therefore CP square is 4 squared, that is 16. So in total, we should find out that 25 equals to AC square plus 16. Here we subtract the 16 from this equation, and find out that AC square equals to 25 minus 16, that is 9. So AC square equals to 9. Here we took out of this equation and found out that the missing side AC equals to the square root of 9, that is 3. So this is side AC, this is equals to 3 units in its length. In the next step, we define the center of this circle. This point is point O. Point P is the point of tendency of tangent PB with this circle. We define the radius of this circle as x. Then we join points O and B together by straight line. Point O is the center of this circle, point B is the point of the circle itself, therefore OB is the radius of this circle, this is equals to x. The radius OB is equals to x, the radius OB is born from point B, that is the point of tendency of tangent PB with this circle. And whenever you have radius that is born to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. PB is a tangent, so PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point C, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point C? We have this angle that is 90 degrees, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we did a construction, that is to say from point O, that is the center of this circle, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. By doing this construction, we get the diagonal OMCB. Inside diagonal OMCB, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this 4 fixed angle in total must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 fixed angle must be equal to 9 degrees in its side. So inside quadrilateral OMCB we have 4 angles, and therefore quadrilateral OMCB is a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So rectangle OMCB, side BC must be equal to the opposite side OM. But BC is 1, and therefore the opposite side OM must be also equal to 1 unit in itself. Likewise, according to the rule, in the same rectangle OMCB, side OB must be equal to the opposite side MC. But OB is x, therefore the opposite side MC must be also equal to x units in its length. What is the length of this missing line segment AM? From the drawing, it is very easy to see that AM total equals to AC minus MC. AM equals to AC minus MC. So AM equals to AC, that is 3, minus MC, that is x. So in total, AM equals to 3 minus x units in its length. In the next step, we join points O and A together by straight line. Point O is the center of this circle. Point A is the point of the circle itself. Therefore, OA is the radius of this circle. This equals to x. So in the next step, we present the Pythagoras theorem on this green right triangle AOM. According to the Pythagoras theorem, this green right triangle AOM, AO squared, this is the square of the hypotenuse, equals to AM squared plus MO squared. Okay, again, this green right triangle AOM, according to the Pythagoras theorem, AO squared, this is the square of the hypotenuse, equals to AM squared plus OM squared. AO is x, therefore AO squared is x squared, and it is equals to AM squared. AM is 3 minus x, and therefore AM squared is 3 minus x squared, plus OM squared. OM is 1, therefore OM squared is 1 squared, it is 1. So we should find out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of this equation, so x squared will get cancelled. After we cancel x squared, this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total we should find out that 0 equals to 10 minus 6x. Here we added 6x from this equation, if I found out that 6x equals to 10. Here we divide this equation by 2, and if I found out that 6x over 2 is 3x, and 10 over 2 is 5. So in total we should find out that 3x equals to 5. Here we divide this equation by 3, and I found out that x equals to 5 thirds. X is the radius of this circle. This equals to 5 thirds units in its length. Our task is to find out the area of this circle. We know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. But we just right now found out that x equals to 5 thirds. If x equals to 5 thirds, it means that x squared must be equal to 5 thirds squared. So in total, the area of our circle must be equal to pi times 5 thirds squared. 5 thirds squared, so it is pi times 5 thirds squared. 5 thirds squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, the area that we are looking for this question, that is the area of this circle, equals to either 25 pi over 9 square units in size. In terms of numbers, the area of this circle equals to 8.73 square units in size. Okay, thank you very much.